The method we were using last section to solve our systems of linear equations, first writing it in an augmented matrix and then writing it in a particular form to read off the solutions, that reduction method is called Gauss-Jordan elimination. So we're going to formalize what that means. We're going to sort of give the exact algorithm for how to perform Gauss-Jordan elimination, and we're going to apply it in cases where it makes more sense to do so. With just as very small systems we've been working with, 2 equations, 2 variables, usually you wouldn't have to resort to these notational time-saving devices, but once you have larger systems, once you're working with 6 or 7 variables, this notation and having a nice algorithm for how to do this becomes very, very handy. So what I have here on the board behind me is a fairly long definition. I've broken it into 2 pieces. Our textbook just gives straight up the one definition, but it's fairly standard to talk about row echelon form and reduced row echelon form is slightly separate things. So here's our definition. A matrix is in row echelon form if it has the following 3 properties. First up, property 1, all non-zero rows are above any rows of all zeros. This just says if you have any rows of all zeros in your matrix, they have to appear at the bottom. Okay, so there's a fairly simple property. 2, each leading entry of a row is in a column to the right of the leading entry of the row above it. So what do I mean by leading entry? By leading entry, I mean if you look at your row and you're reading from left to right, the leading entry is the first non-zero entry you come across. So for example, up in this matrix, I look at this row, the first non-zero entry I come across is that one, reading from left to right. So there's the leading entry of that row. Next row, first non-zero entry I come across, reading from left to right, is that one. And last but not least, look at the third row, first non-zero entry I come across is that one. So those are the leading entries of the row. Our textbook often calls these leftmost entries. I prefer the term leading. And the property is that as you look at your leading entries, they have to appear sort of to the right of the leading entry of the row above it. So this guy is to the right of this one, and this guy is to the right of this one. In other words, we form this nice staircase sort of echelon pattern, hence the name. So your leading rows should always sort of proceed downwards and to the right. Okay, so that's satisfied for this matrix. And lastly, all entries in a column below a leading entry are zeros. So I look at this leading entry, those are all zeros. I look at this leading entry, those are all zeros. And there is nothing below our last leading entry. So all 3 of these things are satisfied. So this matrix, this is in echelon form. So here's what I really want to get into defining reduced row echelon form. Our textbook just calls this, and the homework problems in my math lab just call this reduced form. So a matrix is in reduced form if it's first in echelon form, so it first has to be echelon. But secondly, the leading entries in each non-zero row are all 1s. So all of my leading entries have to be 1s. And you'll notice, well, this leading entry is a 3. This one's a 1, but this one's also a 3. So immediately I know this is not reduced, because my leading entries are not 1s. The textbook usually calls these leading ones, they call them leftmost ones. And second property is, so first you have to be echelon, your leading entries all have to be 1s, and each leading one is the only non-zero entry in its column. So again, these leading ones, textbook calls them leftmost ones. But this also fails this, right? This leading, well, it's not leading one, but this leading entry is the only non-zero entry in its column. So is this one, but when you get to this leading entry, everything above it is not 0. So this is not the only non-zero entry in its column. But if we look at this next example, let's go through this again. That next example, are all non-zero rows above all rows of all zeros? Well, I don't have any rows of all zeros, so it's immediately satisfied. If I did, though, they'd have to be at the bottom. 2, each leading entry in a row should be to the right of the leading entry above it. Well, they're in actually the same position in this matrix. So they sort of, as you proceed down, they proceed to the right, so that's fine. And all entries in a column below the leading entry are zeros. Yes, 0, 0. And that's fine. So it is an echelon. Are all the leading entries 1s? Yeah, everything I boxed here, they're all ones. And is each leading entry, or is each leading one, not only do I need everything below it to be 0, I need everything above it to be 0 as well. Well, sure enough, if you look above them, they're all 0 as well. So it is reduced. This is our goal. Our goal is to take our matrices and put them in reduced form, because once you're in reduced form, it's the easiest form to read off the solutions of the underlying system. So you'll see some homework questions that ask you, is this matrix in reduced form or not, yes or no? And if it's not, it'll quite often ask you, well, what do I need to change, right? Do I need to interchange some rows or add one row to another? What do I need to change? So hopefully going through that process, you'll get pretty good at identifying when a matrix is in reduced row form or reduced row echelon form or not. But yeah, again, before I erase this, I just want to point out that what you're looking for is you're looking for a staircase pattern where your leading entries are all ones, and everything above and below those ones, everything else in the whole column containing these leading ones is 0. That's all you're looking for. And if that's satisfied, then it's in reduced form. So here's our system, and immediately we're ramping up the difficulty here over the last section, right? I've got 3 equations, 3 variables, but I want to solve this system. So first thing I'll do is write down the augmented matrix. I suppose we could call this step 1. Step 1, this is a very simple step, just augment, create the augmented matrix. So we'll construct our augmented matrix. 3, 2, 1, first column, coefficients of, oops, I wrote x3 here, this is of course x1. Second column, I've got 2, minus 1, 3. Third column, I've got minus 1, minus 1, minus 2. And then to the right of the equal sign, I've got minus 7, 3, minus 6. So I have my augmented matrix now. Step 2 is going to be basically what we did last time. I always want to put a 1 right here. In my first column, I'm always going to put a 1 at the top. So step 2, oops. Step 2, place a non-zero entry. Let's generalize this. I'm saying 1 because I have a 1 right now that I can work with. I can just interchange the rows. But if you don't have a 1, just put some non-zero entry up here. If it's 0, you need to get rid of it. All right, so place a non-zero entry in the top left-hand position, A11, and make it a 1 if possible. A 1 if possible, and use it to create all zeros below it. To create all zeros below it. So this is actually sort of several steps that we'll have to do here, but alright, so I want to place a non-zero entry. I have a non-zero entry, but if I have a 1, let's use a 1 instead. So let's interchange row 1 and row 3. Row 1, row 3, we will switch them. So row 1 becomes row 3, or sorry, yeah, row 3 becomes row 1. 1, 3, minus 2, minus 6. row 2 stays the same, 2, minus 1, and 3. And row 1 becomes row 3, 3, 2, minus 1, minus 7. Okay, so that's actually the first part of step 2. The second part is use this entry, so now I have a 1 up there, use it to create all zeros below it. So everything below it needs to be 0, and we can do row operations to do that too, right? So if I want to put a 0 right here, in this 2, this spot where I have a 2 right now, how do I get a 0? Well, I just subtract twice the first row from it, right? This is why having a 1 is nice, because you can just multiply by the appropriate amount. If this is a 2, I need to subtract 2 times 1. So we're going to do row 2 minus 2 times row 1 is going to become row 2. So we'll subtract this off. I have 0, minus 1, minus 2 times 3 minus 1 minus 6 is minus 7, minus 1 minus 4, minus 1 plus 4 is 3. And then we've got 3 minus 2 times, or sorry, 3 minus 2 times minus 6. 3 minus minus 12 is, 3 plus 12 is 15. And that should be the result of that operation. And now I want to do the same thing. I want to put a 0 right here, right? The goal is to put zeros below this 1. And we can actually do 2 operations at the same time as long as we're operating with different rows. I subtracted an appropriate amount from row 2. We can also work with row 3 while we're here. We'll do row 3 minus 3 times row 1. And that'll be our new row 3. So we'll do the same thing on row 3. 3 minus 3 times 1 is 0. 2 minus 3 times 3, 2 minus 9 is 7. Oops, 2 minus 9 is minus 7. And then we've got minus 1 minus 3 times minus 2. So 3 times minus 2 is minus 6. Minus 1 minus minus 6. Minus 1 plus 6 is 5. And then we've got minus 7. 3 times minus 8 is minus 18. Minus 7 plus 18 is 11. Awesome. There's step 2. Put a non-zero entry. Put a non-zero entry in this position. Make it a 1 if you want. If you can, make it a 1. But all we need there is something non-zero, and use it to zero out everything below it by subtracting appropriate multiples of the first row. That's why it's nice to have a 1, because it's easy to see what the appropriate multiple of the first row should be. Now, step 3. The good news is step 3 is really just repeat step 2 again, but on a smaller matrix. So step 3 is mentally cover the first row, because we're done with this leading 1 now. Cover the first row and repeat step 2 again. So mentally, cover the first row and repeat step 1, or sorry, step 2 I should say, step 2 on the resultant submatrix. and repeat this as many times as necessary until you get down to echelon form. So repeat as necessary to echelon form. So I'm just going to pretend this first row isn't here. In my mind, I'm going to keep writing it, right? I'm not going to erase it or anything, but in my mind I'm just going to pretend we're working with just this resultant submatrix, this 2 by 3 stuff that's down below. So 1, 3, minus 2, minus 6. And now we've got this. So step 2 said, all right, now that I'm covering this up, now I'm going to come into this entry. I'm going to look at this entry, and I need to put something non-zero here. Well, something non-zero is already there. I'd rather it be a 1 usually, but I can work with it as it stands. The only easy way I can see to make this as a 1 is to divide through by minus 7. So we'll leave it as it stands, and we're going to use that to zero out everything below it. And the reason I'm going to leave it as minus 7 is because it's pretty easy to see how to use this to zero out the entry below it. We just we subtract it, right? Minus 7 minus minus 7 will give us 0. So I'll just leave this as it stands. Minus 7, 3, 15. So we're going to do, the operation we're going to do is row 3 minus row 2 is going to become our new row 3. So I've got 0 minus 0 is 0. Minus 7 minus minus 7 is also 0. Mission accomplished. We now have a 0 below this leading entry. And then everything else is whatever it is. 5 minus 3 is 2. 11 minus 15 is minus 4. So, turns out we're now in echelon form, but if I had a bigger matrix, I would just repeat the process. Now that I've zeroed everything out below, I've got this leading entry, I've got this leading entry. Now that I've zeroed out everything below this leading entry, I would cover up that stuff, and I'd work with the resultant submatrix. And we'd put a leading entry here, and we'd zero out everything below it. But we're done because we're out of rows at this point. Now we have step 4. So we're going to do basically the same thing, but we're going to work from the bottom right, and proceed back up. So working from the bottom right, working from the bottom up. Working from the bottom up, we're going to look at our leading entries, and then we're going to rescale them. All right, so I'm going to start working with this one, and I'm going to rescale it to a 1. So working from the bottom up, rescale the leading entries, the leading entries to 1s, and use them to zero the entries above them. Okay, so I'm going to work from the bottom up. So now I have this leading entry. I'm going to rescale it to a 1. That's easy to do. How do I get a 1 here? I just divide the whole row by 2, right? So we're going to do 1/2 of row 3 replaces row 3 to give me 1, 3, minus 2, minus 6, 0, minus 7, 3, and 15. 0, 0, 1, dividing by 2, and minus 4 over 2 is minus 2. So I've rescaled that leading entry to a 1, and now I'm going to use it to zero everything above it. So how do I do that? Well, How do I put a 0 right here? I've got a 3 right here. I just need to subtract 3 times the third row. Right? And this is nice because all of these are zeros, so it's not going to affect anything above these zeros here. So we'll do row 2 minus 3 times row 3 is going to become our new row 2. So I've got 0, 0, 1 minus 2. 0 minus 3 times 0 is 0. Minus 7 minus 3 times 0 is minus 7. 3 minus 3 times 1 is 0. And 15 minus 3 times minus 2. Minus 3 times minus 2 is 6. So 15 plus 6 is 21. And then I can do the same thing all in one step, just in this step right here. I've been a bit lazy writing my my little tilde to indicate that these are row equivalent. But in any case, I want to put a 0 up here as well, right? I want to 0 the entry above this leading one. So what do I need to do? If I've got a minus 2, I need to add 2 to it, right? So I can add 2 by just doing plus 2 times row 3. So row 1 plus 2 times row 3 becomes our new row 1. 1 plus 2 times 0 is 1. 3 plus 2 times 0 is 3. Minus 2 plus 2 times 1 is 0. And minus 6 plus 2 times minus 2 is minus 10. Okay, so working from the bottom up, we'll rescale the leading entries to 1s and use them to 0 the entries above them. So, reading from that step, what do I need to do now? Well, I rescaled that leading entry, made it a 1, zeroed everything above it. Now I'm going to come into this leading entry, rescale it, and rescale it to 1 and 0 everything above it. And the good news is that with this, we're just about done, so what do I need to do? I've got a minus 7 here, I want to rescale it, so I'm just going to divide through by minus 7. So we'll do row 2, minus 1/7 row 2 becomes our new row 2. Row 1 is the same. Row 3 is the same. This is what I was talking about with copying errors, by the way. Quite often you're just copying your old rows and only working with one single row. So try to avoid copying errors. But if I divide through by minus 7, we're looking at 0, 1, 0. 23 over minus 7 is minus 3. Last but not least, I use this leading one to make a 0 above it. How do I do that? Well, I've got a 3 here, so I should subtract 3 times the second row, right? So row 1 minus 3 times row 2 becomes our new row 1. I'm going to copy the third row. I'm going to copy the second row because I'm not replacing those at all. I should probably align these a little bit better. And what do I have here? I've got 1 minus 3 times 0 is 1. 3 minus 3 times 1 is 0. 0 minus 3 times 0 is 0. And minus 10 minus 3 times minus 3 is minus 10 plus 9 is minus 1. There we go. This is done. This is in echelon form. All my leading entries are to the right of each other. Everything below them is all 0. And it's in reduced form because all of my leading entries are in fact 1s, and everything above them is all 0s as well. So everything in the columns with these leading 1s is all 0 except for the leading entries. And the reason we've done this is because now you can immediately read off the solution. All right, the underlying equation is x1 equals minus 1, x2 equals minus 3, and x3 equals minus 2. There's our solution to the system. I've long since erased the original system, but now if you want, you can check it, right? You can just go ahead and plug in these values into the original system and check that it is indeed a solution. This is what you'll run into if you're working with a nice system where the number of equations equals the number of variables and it's a consistent system with exactly one solution. You'll end up with something that looks like this: 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, and so on, with just your solutions off to the right. But I want to do another example where we say have infinitely many solutions. Okay, here's another system. We want to solve it. First thing I'll do is write down the augmented matrix. 2, 3, minus 2, just going column by column. Minus 2, minus 3, 3, minus 4, minus 6, 1. Augmentation bar, minus 2, minus 3, 7. All right. What's our algorithm? Put a non-zero entry right here. Make it a 1 if we can, but let's not overexert ourselves to do that. The problem with not having a 1 right here is, okay, it's easy to zero out this entry because I'm just going to add this row to it. But to put a 0 right here, I would have to add a fractional multiple of row 1 to row 2. Let's avoid having to think about fractional multiples. It's really nice, or really easy to put a 1 right here just by rescaling it. If I was introducing fractions along this entire row, I might not do it, but if I just divide by 2, everything in this row is a multiple of 2. So let's do that. Let's take 1/2 of row 1. 1/2 of row 1 will become our new row 1. So we're looking at 1 minus 1 minus 2 minus 1 is our first row. Alright, not officially part of the algorithm. It's not important that we have a 1 right here immediately, but we can see that for ease of calculations, it's nicer to have a 1. So we'll put a 1 right there straight away. Now we'll zero everything out below it. So I need to subtract 3 times row 1 from row 2 and add 2 times row 1 to row 3. So we'll do row 2 minus 3 times row 1 becomes our new row 2, and row 3 plus 2 times row 1 becomes our new row 3. Row 1 will stay the same. This is still 1 minus 1 minus 2 minus 1. Row 2, now what do we have? So we're subtracting 3 times row 1. 3 minus 3 times 1 is 0, as we wanted. If I don't have a 0 there, I did something wrong. Minus 3 minus 3 times minus 1. Minus 3 times minus 1 is positive 3. So minus 3 plus 3 is also 0. It's kind of nice when you get zeros because you know they'll be easy to work with down the road. Then I've got minus 6 minus 3 times minus 2. That's again minus 6 plus 6 is also 0. If I get anything other than 0 here, I'm done. I already know this is an inconsistent system. I can say no solutions, but I think we're going to get a 0 there. We've got minus 3 times minus 1 is minus 3 plus 3 is a new 0. Okay. If we didn't have a 0, we'd be done. That would have been nice, but we have to keep going with this. And now we're doing row 3 plus 2 times row 1. Minus 2 plus 2 times 1 is 0. 3 plus 2 times minus 1, 3 plus minus 2 is 1. 1 plus 2 times minus 2 is 1 plus minus 4 is minus 3. and 7 plus 2 times minus 1, 7 minus 2 is 5. Cool. So now we're looking at this thing. What do I have to do now? So there's my leading entry. Now we cover it up. Now we work with the resultant submatrix. In this column, I need to put a non-zero entry right there. Easiest way to do that is just to interchange these two rows. So we'll just quickly do row 2 and row 3 interchange with each other. 1, minus 2, minus 1, 0, 1, minus 3, 5, 0, 0, 0, 0. Cool. Now I have a non-zero entry right there. I don't have to make it a 1 yet, but it's already a 1, that's convenient. And I use it to zero out everything below it. Well, that's already done. So that step's immediately done, and we can proceed. Now we cross out, mentally sort of ignore the first two rows, and we proceed with the last row, and you can see that we're not going to have any leading entries in this row. It's a row of all zeros. So we're done. This is now in echelon form. To put this in reduced row echelon form, now we look at our leading entries and proceed from the bottom up. So I'll look at this leading entry. I'll make it a 1 if it's not already a 1, but it is, and I'll use it to zero out everything above it. So last thing I need to do is zero out the entry above this guy, and I can do that just by adding row 2 to row 1. So row 1 plus row 2 becomes our new row 1. I'll copy everything else before I do that. 0, 1, minus 3, 0. Oops. Like I said, be careful not to make copying errors. 1 minus 3, 5. And we're adding row 2 to row 1. So 0 added to 1 is 1. 1 added to minus 1 is 0, giving me exactly what I wanted there. Minus 2 plus minus 3 is minus 5. And minus 1 plus 5 is 4. This is in reduced form. Why did I do that? Well, again, because this is the easiest form to read off the solution set. Unfortunately, this is the harder case where my number of leading entries, my number of leading ones, doesn't match the number of columns. I don't have a leading entry in every single column, so what this means is we have infinitely many solutions. So let's write down what they are. Let's write down the equations first. I've got x1 plus 0 times x2 minus 5 times x3 is 4. And I've got 0 times x1 plus x2 minus 3 times x3 is 5. There's lots of different ways you can write the solution now. What we usually agree to do is we agree to let the column corresponding to the column that doesn't have a leading entry in it, we agree to make that the corresponding variable, we agree to make that corresponding variable the parameter. Okay, so solve for x1 and x2 in terms of x3. Again, the reason I'm choosing x3 is because it doesn't have a leading entry in its column. All right, so that's the reason I'm choosing this one. So that gives me x1 is 4 plus 5x3, and x2 in the second equation is 5 plus 3x3. And my solutions then are, I'm going to let x3 be my parameter, k, or t, or s, or whatever you want to call your parameter. x3 is k, and that means that x1 then is going to be 4 plus 5k, and x2 is 5 plus 3k. Or you could write this as a point, right? As really a parameterized set of points. 4 plus 5k, 5 plus 3k, and k. You'll notice that's a point with three coordinates. It's actually a point in three-dimensional space. So anyway, this is what happens when you don't have a leading one or leading entry in every single column. Then you're either looking at infinitely many solutions, or you might have a leading entry sort of over here to the right of the augmentation bar, which would of course mean you have 0 equals some non-zero number, and you're looking at an inconsistent system. This is Gauss-Jordan elimination. The more you do of it, the better you'll get. It's really not as slow as I've been doing it on the board. It takes me a little while because I have to explain it as I'm going. But if you're doing this on your own, if you're just going through the motions and sort of reducing the matrix on your own, you'll find that it's actually a fairly quick, fairly clean process. The more you do though, the better you'll get, and the faster you'll get. So I recommend lots of practice. So that is it for this video, but as far as practice goes, we could be doing these all day. We could do lots more examples of these. I could do an example where you end up with an inconsistent system. I could even do an example where you end up with 2 rows of all zeros, and you only have 1 leading entry, and that means you would have to parameterize x2 and x3. So x2 might be s, and x3 would be t, or something like that. There are examples like this in the textbook. I'd recommend reading them, going through them, just to see more examples and get more practice with this. But we'll stop here. Thank you.